His the main research interest is in number theory in a very broad sense, of course, number theory and mathematical physics and quantum chaos. In fact, of late, I see that he is kind of doing a lot of work in the interplay between number theory and quantum chaos. And he is also recipient of many uh, awards and is a prolific researcher. And above all, he is a wonderful speaker. That's one of the things that when the conference came up, I thought I will invite Z purely if he agrees. And I'm so grateful to him that he has accepted our offer immediately, in fact. And so I request Professor Z to go ahead, and we are all waiting for your. Thank you so much, Professor Z.
Okay, thank you for the invitation. Thank you, all the organizers, for this great effort, and especially to Kalyan Chakraborty for organizing this. I know it was not an easy thing to do. I actually attended several of the lectures, either live or with time delay, and found several of them very inspiring and educational. And I hope this meeting will help launch this institute into the next stage of development. And my lecture will be partly educational, and the first few slides, at least, will be very familiar to the experts, but I hope that within 4-5 slides or so, we will get to a new problem. This lecture is purely number theory. To my knowledge, it has no connection with mathematical physics, but nonetheless, I hope you will find it of interest. So let me remind everyone what is known about the distribution of prime numbers. So first of all, we've known for many, many centuries and millennia that there are infinitely many primes. And if you want a quantitative version of this, then you ask how many primes there are up to a given number. And here is this function which counts the number of primes up to a given number, and it's an increasing function because we know there are infinitely many primes. And the question that people asked themselves over 250 years ago at least was, how does this function grow as a function of x? How does pi x change with x? And eventually Gauss formulated a conjecture which is now called the prime number theorem. So let me describe what was known about it. In 1850, Chebyshev showed that pi of x has order of growth x over log x. And he proved an upper bound and the lower bound, which were of the same quality, but with constants which did not match. The conjecture was, among other things, that the constants should be 1. And this was proved by Hadamard and Delavallee-Poussin in separate work in the end of the 19th century. And this is called the prime number theorem. And it says that pi is asymptotic to Lie, where this notation asymptotic means that the ratio has a limit and the limit is 1. And Lie is this logarithmic integral, which to leading order is x over log x, but then there's other terms which, for instance, there's an x over log squared x, and so on in decreasing powers of log x. And here is a match between pi of x, and here is the difference between Lie and pi. And you can see that not only is the ratio asymptotic to 1, but in fact, if you look at the difference is very small. So roughly speaking, the width of this column, which measures the difference between Lie and pi, is about half the width of the column which measures pi, which leads us to conjecture that not only is pi over Lie tending to 1, but in fact, the difference is of order square root of x, and this is known as the Riemann hypothesis. It's not the standard version that you may see written, but it is completely equivalent to it. And here is the numerics, which I think is very convincing that the Riemann hypothesis is correct, but to date, I at least do not know a proof of this. I will need a weighted version of the prime number theorem, and that's the one that anyone who works in the subject finds most useful. This logarithmic integral is an awkward function to deal with precisely because it has secondary terms. And what you do, you replace the crude count of the number of primes by a weighted count. So you count not just primes, but prime powers. You count all prime powers and weigh each prime power with the logarithm of the prime that is associated with it. This is called the von Mangold function. Then instead of looking at pi of x, which is the number of primes up to x, you look at the sum of all prime powers up to x, each weighted by this von Mangold function. And the prime number theorem, and the way I've stated it, that pi is asymptotic to lie, is equivalent to saying that psi, which is the function that Chebyshev introduced, is asymptotic to x. So it's a much nicer asymptotic. And the Riemann hypothesis is equivalent to the claim that psi is x plus a remainder, which is of size roughly x to the half. Okay, so this is some general background on the beginnings of prime number theory. And here is the standard way that people formulate the Riemann hypothesis. It is irrelevant to my lecture, but I wanted to make sure everyone is on the same page here. So instead of looking at the remainder term in counting primes, Riemann had the idea of looking at the Riemann, what is now called the Riemann zeta function. And it's a function which is initially defined for s bigger than 1. You can take s to be complex as the sum of all inverses of the s power of the integers. It has a product over primes. This is called the Euler product, and it explains why it is relevant to the theory of primes. And even though the sum and the product only converge absolutely when s has real part bigger than 1, Riemann showed that in fact this function has an analytic continuation. You can make sense of it for all complex s, except when s is 1, when this is clearly infinite. And at s equals 1, it has a simple pole. And in addition, this function has a functional equation which relates its value at s to its values at 1 minus s. And the Riemann hypothesis is the statement that all the zeros, which are not trivial in some sense, lie on the center of symmetry of this functional equation, which is the line having real part of s equals a half in the complex plane. So this is completely equivalent to my earlier formulation of the Riemann hypothesis in terms of the remainder term in the prime number theory. Okay, so this is what we want to know about prime number theory. So now I want to go back to something much more basic and discuss the least common multiple of the sequence of integers from 1 to n. So let me just review what is the least common multiple. So if we're given a number of integers, the least common multiple of these integers is the minimal integer which is divisible by all of them. So in other words, you want this integer to be divisible by all of these AI, and to be minimal, if you have another such integer, then it is divisible by your least common multiple. So for instance, the least common multiple of two integers is just the product divided by the greatest common divisor. And there's a formula for the least common multiple in terms of the prime factorizations of the integers involved. So if you make a list of all the primes dividing the integer, each of them comes with a certain exponent, and then the least common multiple will have a prime factorization where the exponent of the primes is the maximum of the exponents of all of the integers involved. So for instance, if to compute the least common multiple of 60, 378, and 75, we factor each of them. So 60 is 4 times 15, so 2 squared times 3 times 5. 378 has this prime factorization of 2 times 3 cubed times 7. 75 is 3 times 5 squared. And then for each of the primes involved, you look for the biggest exponent possible. So for the prime 2, 60 is divisible by 2 squared, so we have an exponent of 2. 378 is divisible just by 2 to the 1, not by 2 squared. And 75 is not divisible by 2, so we keep the exponent 2. For the prime 3, we search here and we see that all of them are divisible by 3, but 378 actually is divisible by 3 cubed, which is the top exponent. So we keep 3 here in the exponent. And then for 5, 75 is divisible by 5 squared, and 5 squared is the maximum you can do. So you keep 5 squared, and then you have a 7 coming from 378. So the least common multiple of these 3 integers is a number whose prime factorization is given by this formula. Okay, so this is not a feasible way to compute least common multiples, but it's theoretically very important for me. And the first question I want to ask is, what is the least common multiple of the first n integers as a function of n? Okay, so this is a good exercise to do if you haven't done it before. I will not do it, even though I can, but it's something that you can do by hand, and I'm sure the director of the institute will offer a valuable cash prize to anyone who does it first correctly. It turns out that Chebyshev was playing around with this, which is why which is the connection to the previous story. So what he showed was that the least common multiple of the first n integers is exactly this question that I showed you before, namely it's the Chebyshev function psi of n. So it's, again, the weighted count of all prime powers, each weighted by log of p. So this is not an asymptotic, it's an exact formula. It's an identity, and therefore an analytic number theorist would say it's trivial because it's an identity rather than an estimate. Okay, so the prime number theorem, if you believe the prime number theorem, it says that psi of n is asymptotic to n. And here is a numeric that shows, I plotted, not psi of n, sorry. This is a mistake. This is the log of psi of n. Let me very quickly put the log in here so that you don't. Okay. And here is a plot of log of the least common multiple of the first integers as a function of n, and you clearly see that it grows linearly, which is what the prime number theorem says. So far our numerics don't tell us anything that we don't know theoretically. Okay, so this was gained is, I think, due to Chebyshev. The identity is very easy, but the prime number theorem was not known to him at the time. It took another almost 45 years until it was proven. Okay, so now I am arriving at the question that I want to discuss today, which is the least common multiple, not of the first n integers, but of the first n values of a polynomial. So you take a polynomial, let's say the polynomial x squared plus 1, and look at the least common multiple of the first n values. Now, if your polynomial is something simple like x times x plus 1, then again, I leave it as an exercise to show from what we know until now that it is easy to compute the least common multiple. And again, it turns out to be to grow linearly with a constant that depends on which specific split polynomial you take. So for instance, for the polynomial x times x plus 1, that multiple is 1. So the log of the least common multiple in this particular case of x times x plus 1 will be asymptotic to n. For other polynomials of this form, which factor over the rationals, it will be a different constant, but it's very easy to compute this constant from what we know today. The interesting case is when the polynomial is not a product of linear factors, in particular if the polynomial is irreducible over the rationals and has degree bigger than 1. And Javier Siluelo, in a paper that was published in 2011, conjectured that in this case, the log of the least common multiple doesn't grow linearly, it grows quicker. It grows like n log n with a prefactor, which is the degree minus 1. So when the degree is 1, you don't see this term. But for higher degree, you will see this term. So it's quite shocking to me that it was only in 2011, if we compare it to Chebyshev, which was 1850, that anyone looked at this and made an interesting conjecture about it. Unfortunately, Javier Siluelo passed away a few years ago at a young age. At least for me, this counts as young. But the conjecture, I think, is very interesting. And what I want to do is tell you about this conjecture. What's known and mostly what's not known. So what Siluelo did prove is the case of degree 2. So he proved that if you take a polynomial of degree 2, for instance, x squared plus 1, which is irreducible over the rationals, then indeed the log of the least common multiple of the first n values is asymptotic to 1 times n log n. When n tends to infinity, he actually did something more. He got a secondary main term. So he showed that not only is the log of this least common multiple asymptotically n log n, it's equal to n log n plus some multiple of n, which depends on the polynomial, plus lower order terms, which we know nothing about. The main term, to get the main term, actually, in this case, turns out not to be hard, and I may indicate to you how to do it. The secondary term is much deeper, and it required quite very deep theorem about the uniform distributions of solutions of quadratic congruence modulo primes, which was only known due to Duke, Friedlander, and Ivanets in the mid-1990s. For higher degree, for degree 3, for instance, the conjecture is completely open. There isn't a single case of an irreducible polynomial of degree bigger than 2 where we know how to prove this conjecture. Now, I don't know if this is very difficult because, as you can see, the conjecture is from 2011. If you remember, the Riemann hypothesis is from around 1858 or so. So much older. So on the scale, on the time scales of number theory, this is a very young conjecture, but it's nonetheless an interesting conjecture, and I found it quite fascinating. So let me show you some numerics. So in this meeting, we had a really fascinating lecture from Professor Ashok Sen, who was at least on paper a physicist, and physicists like to do experiments. Number theorists also like to do experiments. So I will show you 2 experiments. One is for a case where I know the theorem. So for this irreducible quadratic polynomial x squared plus 1. So here is a plot. So the solid blue line, which in the top row you can't really tell from the orange line, is the empirical experiment. I took log of the least common multiple of the first n values of this quadratic polynomials and plotted it. I took here in the plot, I only displayed what happens between 0 and 100,000, and then inset is what happens between 95,000 and 100,000. In the first plot, you see that the theory is n log n. So it's a theorem, we know this. This is something we know. You can't distinguish the blue line, which is the experiment, from the theory, which is n log n. But if you zoom in, if you look at what happens between 95,000 and 100,000, then you can clearly see that the theory overshoots. N log n is slightly bigger than log of the least common multiple. Okay, and in this second picture, I plotted the difference between the experiment and the theory. So the jagged line is log of this least common multiple, and the orange straight line is, the blue line is the difference between log of L of this least common multiple and n log n. And the orange straight line is this theoretical value for the secondary main term, and you see a reasonably good match, which of course is a theorem, so it's not surprising that you see a good match, but again, it's not a complete perfect fit, but there are fluctuations around it. So now let me show you what the experiment looks like for a cubic polynomial where we don't have a theorem. So this is roughly the same experiment. So for the cubic polynomial x cubed plus 2, which is irreducible over the rationals. So the blue line is the log of the least common multiple of all the first million integers. And the red line is the conjecture, which is twice n log n. And it looks like a quite reasonable fit. Of course, it starts overshooting the theory, as it did in the quadratic case, but it overshoots it more drastically in the quadratic case. This picture seemed to be the same. So here I've plotted in the second picture the difference between the experiment and the main term in the conjecture, which is twice n log n. So here in the first picture, they seem close. When you zoom in, they're not that close. And you see that this difference looks like a straight line. So that indicates that there should be a further conjecture that says not only is log of this least common multiple asymptotic to twice n log n in the cubic case, but there should also be a negative secondary term, which is linear in n, so a constant times n. Okay, but even the 2n log n is not a theorem at this point. So we don't know this for sure. Okay, so let me tell you what we know for general polynomials. So first of all, for any polynomial, for any irreducible polynomial, we know that the log of this least common multiple is bounded above by the right constant times n log n, up to lower order terms. So this is something that we do know. It's implicit from what Thiele-Oeler did. I will even indicate this. And what we now know is that we also have a lower bound, definitely for any irreducible polynomials, in fact, for anything which is not a product of linear terms over the rationals. We know that the log of the least common multiple is bounded below by a constant times n log n, up to lower order terms. So this is really new. This is something that I noticed with James Maynard, who was visiting me in Tel Aviv a year ago or so. So people have thought about this before, but all that was known was a linear lower bound, but this, which was off from the conjecture. We now know that we have both a lower and upper bound of the same quality for this log of the least common multiple. So at this point in life, we are similar to where Chebyshev was in 1850 when he was studying pi of x, he had upper and lower bounds for pi of x, which are of the right order of magnitude, but in his case, the constants were wrong. In our case, we have the upper bound with what we think is the right constant, but the lower bound we don't have with the right constant. Our argument gives a constant which is 1 over the degree. The conjecture is that the constant is the degree minus 1. Our constant was improved about 2 days after we posted it by a young undergraduate at MIT called Ashwin Shah. You replace our constant by a different constant, but it's still not the correct constant. So the conjecture stands for now. And I want in one slide, 1 or 2 slides, just to explain what this conjecture is related to. So there's a relation to the distribution of small roots of congruences. What Tiliaruelo did was reduce the computation of this log of the least common multiple to a certain problem about polynomials having more than one small root modulo big primes. So here is Tiliaruelo's formula, or something that you can, if you stare at his paper, is there. And what he proved was that the log of this least common multiple is what we want it to be, which is the degree minus 1 times n log n, plus something which is negligible relative to that, minus some constant times log n times a certain quantity, and that quantity counts the number of primes bigger than n, for which this polynomial has 2 distinct small roots, where small means less than n. So the prime is bigger than n, and we want the polynomial to have 2, at least 2, maybe more, small zeros modulo p. And small means smaller than n. P is bigger than n, and so these are small. Okay, so if we knew that if we can control this number of primes, then we can prove this conjecture. Now, if you just look at Tiliaruelo's formula, I didn't tell you how to do it, but if you believe it, then it is clear that it gives an upper bound of the right order of magnitude, because here there's a negative sign. We're subtracting a quantity which is manifestly non-negative. So if you forget about it, it says that log of this least common multiple is at most d minus 1 n log n plus the lower order terms. So that gives you the upper bound. And moreover, it tells you that the conjecture, that the main asymptotic, is equivalent to showing that the number of such primes is growing slower than n. So all I have to do is show that, to prove the conjecture, is show that if I give you an irreducible polynomial, to show that it doesn't have more, it has less than n small primes, where it has 2 distinct small roots. So what is easy here, I want to explain it, is to show that it has at most n. But it is useless for us because we want the growth to be slower than n. We want the limit of s of n over n to tend to 0. So this is just saying that the limit is bounded, but that's not going to help us. Another easy thing, and this is what Tiliaruelo did, is to show that when the degree is 2, for instance, for x squared plus 1, not only is s of n little o of n, s of n is actually 0. It turns out that for quadratic polynomials, there are no primes bigger than n for which there are 2 distinct small roots. So let me just show you this because it's so easy. Okay, so this is the quantity I want to show 0. So I count the number of primes bigger than n. I want to show there's no such primes. for which there are two integers less than n, for which f of m and f of n are divisible by p. So this is a simple check. This is the only technical slide in this lecture. So suppose I have such a prime. So I have two integers, small integers, m and n, for which p divides both f of m and f of n. So in particular, it divides the difference. So now this is true for any polynomial, and now I substitute the polynomial s squared plus 1, and then the difference of m squared plus 1 and n squared plus 1 is m squared minus n squared, which factors as m minus n times n plus n. Now, if a prime divides a product, it has to divide one of the factors. So p divides either m minus n or m plus n. But I'm assuming that m and n are small. So that means both this difference and the sum are small. In particular, they're smaller than 2n. And if p is large, then it cannot divide a small number. And therefore, this quantity is 0 in this case. So that's how Thiele-Euler showed that for irreducible quadratic polynomials, the log of the least common multiple is asymptotically n log n. As I told you, he actually did more. He gave a secondary main term, which is of size n, but this is much more complicated. I just wanted to show you something easy. Okay, so I have to disappoint you in admitting immediately that I don't know how to prove this conjecture. So I know a lower bound, which is off from the right size. I know an upper bound, which is of the right size. So let me tell you two things that I do know. And this is, again, very recent work. And this is something that I did with my student Sal Zehavi. This is his mugshot here. So what we decided to do is, instead of looking at the individual polynomial like x cubed plus 2, to look at random polynomials, in the sense that I take my favorite polynomial, for instance, x cubed plus 2, and add a constant term, and take that constant term random in a certain sense. So, of course, if I start with an irreducible polynomial like x cubed plus 2 and subtract 2, I get x cubed, which is not irreducible. So I may be out of the context which we want. But it turns out this is a rare occurrence. It is a computation that you can do that for most values of this constant that you add or subtract, you don't change irreducibility. The number of a's up to t for which your fixed irreducible minus a is reducible is at most square root of t, so much less than the number of possible a's. So I just ignore this issue. I'm allowed to ignore this issue. Okay, and the quantity I want to study is the log of this least common multiple of this shifted polynomial evaluated the first n integers, and I would like to individually show that it is asymptotic to n log n times the right constant, but this I don't know how to do. So what we decided to do was to at least prove this for most of the polynomials, most of the shifted polynomials, and the result is that for almost all of these shifts, meaning you let t grow, but we're constrained, t has to grow at a certain rate together with n. There are now two parameters, there's capital N and there's capital T, so they grow together in a certain restricted sense that's written over here. But given that, we can show that for almost all of these shifted polynomials, we indeed have the right asymptotic. Okay, so this is one indication that the conjecture is true, in addition to having some numerical support. that it holds, at least in a certain sense, for almost all irreducible polynomials. So that's one thing that I know how to do. I want to tell you in a few minutes of another thing that I know how to do. And this is to change context. Okay, right now, I can't solve the problem over the integers, so I move to a different context. I replace the integers with polynomials over a finite field. So there's an old and long-standing analogy between number fields and function fields, and it's a very fruitful analogy. So even though we don't know the Riemann hypothesis for number fields, we do know it for function field, and this is the work of André Weil from the 1940s. And so it's a useful idea to try to change context, formulate a similar problem in a function field context, meaning for polynomials over a finite field, and see what you can do with this new problem. So what do I mean by polynomials over a finite field? So you take a finite field, for instance, you take a prime and look at the integers modulo that prime. That's a finite field. You can have finite field where the number of elements is any power of a prime, but it's no longer the integers modulo q. It's an extension. And then we consider all polynomials with coefficients in this finite field. Let's think with coefficients in the integers mod 3. And these form a ring. You can add, you can multiply, you can talk about divisibility. You have a Euclidean algorithm. You have divisibility with remainder, as we all know, for polynomials with coefficients in any field. And so they serve as an analog of the integers, and there's a dictionary that you can form. For instance, the analog of primes are irreducible polynomials. We usually talk about positive primes. We don't think of -2 as a prime, even though for all purposes it functions the same way as +2. And for polynomials, the way you say positive is to talk about monic polynomials. So instead of multiplying a prime by ±1, which is an invertible integer, you can take a monic polynomial and multiply it by invertible polynomials, which turn out to be scalars, and get all polynomials that way. And in both cases, we have the fundamental theorem of arithmetic, which gives you unique factorization into primes in the case of integers and into prime polynomials in the case of polynomials. So these are qualitative analogs. There are also quantitative analogs. There are several of them, but let me just list one of them. It's called the prime polynomial theorem. So we talked about the prime number theorem. The prime polynomial theorem is similar. It counts the number of monic irreducible instead of positive prime. And instead of saying of size up to x, we specify the degree. You can say the degree is at most something or exactly something. It turns out not to matter. And the prime polynomial theorem is a statement that the number of such monic irreducible of given degree is the total number of monic polynomials of that degree, which is q to the n, divided by its logarithm in the correct base. So that's called the prime polynomial theorem. It is a theorem. It is actually an easy theorem. This was known probably 100 years before the prime number theorem. And not only that, we actually know this with the remainder term, which is size square root of the main term. And I told you in the case of integers, this is exactly the Riemann hypothesis. Here, this is an easy fact. It's sort of the Riemann hypothesis for curves over a finite field when the curve is that fine line, and then there's some degenerate thing that happens, and so it's quite easy. Once you take the analog for curves of higher genus, this is no longer easy, but it is still known, but it's a completely different level. Okay, so this is the new context that I want to discuss my problem. And so let's formulate the analog of this least common multiple problem for polynomials over a finite field. Okay, so you start with a polynomial with coefficients in this ring of polynomials. So for instance, I should have written an example. Let me write down an example. So for instance, you can take f of x to be the polynomial x squared, not plus 1, that's not so good, it may factor, but x squared minus t. So the coefficients are 1, 0, and t, which is your extra variable. So this is a polynomial which is irreducible over the ring of polynomials, over the field of rational functions of t, because t is not a square root of anything in this field. And now, so take this polynomial, or your favorite such polynomials, and evaluate it not at the first n integers, but at the first several polynomials when you bound the degree. So if degree bounded by something. So that's the analog of evaluating your polynomial like x squared plus 1 at the first n integers, which are positive and bounded by n. Here we substitute polynomials in T, which are monic, that's the analog of positive, and the analog of bounded by n is bounding the degree. And I want to calculate this least common multiple. So it's exactly the analogous quantity to what we're doing over the integers. And the conjecture that one can naturally put is that the log of this, okay, I'll say something that's not correct. The log of this should be asymptotic to the degree minus 1 times n log n. Except I haven't said what is capital N. So capital N will be the number of such monic polynomials of degree exactly nu, so that's capital N. I take log base q of this, so it's just the number nu, it's the degree I'm bounding. And I can't talk about log of a polynomials, but log functions the same way as the degree. Log of a product is the sum of the logs. The degree of a product of polynomials is the sum of the degrees of these polynomials. So what I think is the correct analogy of the conjecture that we had for integers is the statement that the degree of this least common multiple is asymptotic to d minus 1, where d is the degree, I should say this, d is the degree of in x of f, sorry. I did something which is a bad thing, my apologies. Okay, so let me write here that d is the degree in x of polynomial f. So for instance, in the case of the example that I showed you here, d is 2. Then the conjecture would be that the degree of this least common multiple would be d minus 1 times q to the nu, which is capital N, times log base q of q to the nu, which is nu. So that is the natural analogy of this conjecture. So I don't know how to prove this conjecture either, but at least what we know are a few examples. So in my final slide, I will just tell you an example that where I can prove it. So I can prove it in degree 2. but this is exactly the Taylor-Euler proof. I told you how to prove it for the integers. The same proof works word by word for polynomials, and it's a good exercise to do so. But unlike the case of the integers, we do know some higher degree cases here. And this is work of my student Itai Leumi. This is, in this picture, he looks like a fugitive from an asylum for the criminally insane, but he's actually quite a pleasant guy. I will tell him to change the photo on his webpage. The result is that, let's look at the polynomial like x cubed minus 2. But here I have another parameter. The parameter is the size of the finite field, and I take the size of the finite field to be congruent to 1 modulo d. So for instance, if d is 3, then q will be 1 modulo 3, but not 2 modulo 3. And a is any non-constant polynomial, which is not a perfect pth power for any prime divisor of d. So if d is 3, just saying that a is not a perfect cube. In the case of a perfect cube, you will be in trouble. Let me show you why you will be in trouble. Because if you take a to be a cube, let's say a to be b cubed, then this is clearly reducible. So it's a bad thing to do. It's not, we don't want this example. Okay, so this is why this is a good condition to put in. It's not an artificial condition. Q equal 1 mod d is a trick. And then the statement is that if you are not of this form, that is, if A is not a perfect pth power for any prime divisor of d, then the polynomial is irreducible, it's separable. This is a known thing, this is not new. And we know the conjecture in this case, the degree of the least common multiple is indeed asymptotic to d minus 1 n log n, where n again is the number of, it's q to the nu, it's the number of monic polynomials of degree nu, exactly. Okay, so this is an instance of this conjecture being provable, at least in a case where it's not known over the integers. Now, Itai has been working on this for a couple of months now. He actually has a few more cases where he knows this theorem, where he can prove the conjecture, which are different in this case here, but I decided not to overload the presentation with too many details. So I think this is a good place for me to stop. So thank you very much for your attention.
Yeah, thank you, Mr. Rudnick. It was such a wonderful talk, and especially it is so because we have just about 10 students got enrolled into our MSc PhD program, and they're just beginning of MSc first year, just started, not even the course started. So I'm sure they're all sitting here. They have enjoyed this talk very much. Thank you so much, Mr. Rudnick. And so first, our and then hello.
Very good, very good. Pleased to see you.
To that, you consider the LCM of polynomial.
I'm sorry, I'm having trouble hearing you. Can you speak up?
Go to the slide.
I still have trouble hearing you. Why is this? Oh, much better.
Yeah, is it okay? Ask me that go to the slide where the polynomial is shifted by an integer. The LCM of polynomials shifted by an integer. In some one of the slides you were talking about that.
Again, which one? I still can't hear.
Yes, polynomial.
So the random polynomial case.
Ah, the random polynomial, yes.
Vishnu. Yeah, so what is the question? Yes, shifted by any. Yeah, so what you are saying that when you are shifting by this integer a, we have to make sure that it doesn't become 0. So
Yeah. Yes, I definitely want to make sure that it doesn't become 0. And I also want to make sure that this shift is irreducible. Now, if the shift is irreducible, then it cannot become 0, because if you have a rational 0, an integer 0, the polynomial is reducible.
yeah, so what is saying that you can't consider any general irreducible polynomial for this. So you may have to consider some specific type of irreducible polynomial to make sure that it doesn't happen. It doesn't become.
So again, if what we show here is that there could be, so let's take the polynomial x squared plus 1. And if you shift x squared plus 1 by 1, you get the polynomial x squared, which is reducible. Or if you shift the polynomial x squared plus 1 by 2, you get the polynomial x squared minus 1, which is not only reducible, but which actually vanishes here, which is what you worry about. But if what we can show is that for most shifts, in fact, for all by the square root of t of the shifts, the shifted polynomial is irreducible, and therefore none of these integers will be 0. So we throw away those a's for which f naught x minus a is reducible, and then none of these numbers are 0, and we can form the least common multiple. So implicit here in the definition that we have to throw out a small number of a's where we can't even compute this quantity, as you said quite correctly. But as long as we show that this number is small relative to the number of possible a's that we look at, for the random statement, we are still in good shape.
Any more from the audience?
I have a question. May I ask?
Yes, please.
In the same problem, so this you have actually.
Who's this speaking? Manju?
Yes, Manju.
Hi, Manju.
It was a great talk. Yeah. So I have one question about what is the technique here. So you have an upper bound for every single A of the correct order, right? So do you somehow study the average of this log of L over A? And is that how?
This is the next slide that I was hiding. What we show is, so we know for any polynomial that this log of the LCM is the right quantity plus something which is bounded by quantity controlled by, this number of big primes. This quantity I called S of A. And what we show is that for almost all A, this quantity is smaller than N, which is what we need, by actually just bounding the mean value.
Okay.
Which is sufficient because it's a positive quantity.
Okay.
As a probabilist, you appreciate this. I don't do a variance computation. I just do a first moment.
Yeah. Right.
So of course, how to do this is a detailed thing, which has to do with prime number theory, but it's not very sophisticated.
Okay. Thanks. I have another question, possibly very naive, but does it make sense to look at this problem inside arithmetic progressions or something like that?
You can look at the values. You can certainly try this. So for instance, here, instead of looking at the first n integers, just look at the first n elements of an arithmetic progression. But it turns out to be the same problem because it just means you've changed your original
Oh, the
polynomial
polynomial.
to another one.
Yeah, of course. Thanks.
Yeah.
Is there any more questions from our Zoom link participants? So you can please unmute yourself and ask the question. Yeah, so if not, then we will go to the YouTube chat. Is there any question from YouTube viewers?
Sir, there are no questions from the YouTube chat box.
Okay, so it's fantastic. So I think Professor Rudnick, this was a wonderful talk, and the conjectures look so tempting. So I'm sure that quite a few students who are present here, even if they're students, they will pick this up and will try their best.
Yeah, I'm looking forward to having a solution.
Yeah. So people should be in touch with Professor Rudnick if you get anything like that undergrad student who did. I mean, in fact, he has become already very famous for that. And so we expect some of you really to pick that one up. Thank you so much, Professor Rudnick, and we'll see you sometime here. I hope that when normalcy returns, you should visit us.
Thank you, and thank